SpaceTime is brought to you in collaboration with Australian Sky and Telescope magazine, your window on the universe. You can download SpaceTime as a free twice-weekly podcast just about everywhere, including iTunes, Stitcher, Pocket Casts, Bytes.com, YouTube, SoundCloud, Audio Boom, and from spacetimewithstuartgary.com. The show's also broadcast coast to coast across the United States on Science 360 Radio by the National Science Foundation in Washington, D.C. Coming up on SpaceTime, a new test for cosmological inflation, more mystery surrounding an already strange star, and a subsurface ocean discovered on Saturn's moon Dione.
Welcome to SpaceTime with Stuart Gary.
When the universe first burst into existence in the Big Bang 13.8 billion years ago, something must have happened during those first nanoseconds that caused it to suddenly expand from a singularity of infinite density and virtually no dimensions into the cosmos we see today. Scientists call this mysterious event cosmological inflation, and it explains why the universe looks pretty much the same in all directions. The problem is, scientists really have no conclusive evidence that cosmological inflation ever existed, what it actually is, or for that matter, what physical mechanisms are likely to have driven it. Now, a report in the journal Physical Review Letters and on the pre-press physics website archive.org claims hypothetical clumps of dark matter, known as mini-halos, could provide a new way of testing theories on cosmological inflation. Dark matter mini-halos are hypothetical ultra-compact clumps of cold dark matter, a mysterious substance which astronomers can't see, but which they know exists because of its gravitational influence on normal matter. The authors believe these compact halos of dark matter would have formed just after inflation ended, and so they may retain some information on the early universe not accessible through observations of the cosmic microwave background radiation, the leftover heat from the Big Bang, which is now cooled to just 2.7 degrees above absolute zero. The authors analysed constraints on the likely size and density of mini-halos derived from observations of gravitational lensing, gamma-ray bursts, and the timing of pulsars. One of the study's authors, Hamish Clark from the University of Sydney, says such quantities could be related to important parameters of inflation, such as the shape of the inflationary potential.
When we look out at distant galaxies, we can see that they all appear to be moving away from us. And this is due to an effect that we call cosmological expansion. So you might be tempted to think that this is due to a massive explosion and everything's rushing away from us. But in reality, it's just that the space between things is increasing. So you can imagine if you're an ant standing on a balloon and there's a bunch of different dots drawn on the balloon and the balloon starts to inflate, then the ant would see these dots moving away from it no matter where it's standing on the balloon. So it's actually, in this analogy, the balloon surface is space-time, and it's the distance between things that's expanding. So at the present day, it seems like cosmological expansion is fairly constant, but in the very early universe, there was this rapid period of extreme expansion. To get a sense of the scale of this expansion, if you had something that was about the size of an atom and before the expansion occurred, and then compare the size of it after, it would be the size of the observable universe. And this expansion would occur in 10 to the negative 35 seconds, so that's 0.3501 seconds. So it really is this crazy, huge change in the state of the universe from a hot, dense state into a much more diffuse one. So that's what we call inflation.
And it's been an important issue because something must have happened, because no matter which direction in the universe you look at, it all looks pretty much the same in all directions. And normally when things evolve, you wouldn't expect them to evolve quite that smoothly in all directions. There'd be more lumps in one area or something like that. That didn't happen. Something must have happened really early on to allow the universe to expand to a massive extent before things had a chance to evolve along their own tracks. And that's really why we have this theory of cosmological inflation.
Yeah, exactly. Like the majority of structure in the universe, so the galaxies or larger scale structure than that, was formed by these small wobbles in density that occurred before inflation. And so the reason it's so homogeneous everywhere is just because it was blown up to an extent that the distance between these wobbles was much larger than what we can see. And so if inflation didn't occur, you would get large hot areas on one side of the universe and cold areas on the other. It wouldn't be as homogeneous as we observe it.
Yeah, of course, for a while there, they thought they may have found some sort of lack of symmetry when they looked at the cosmic microwave background radiation, but then they realized they were simply seeing part of the universe in the direction of a particular well-known supercluster of galaxies, which sort of would explain that. So we still have this homogeneous look to the universe. What sort of models have there been to explain how cosmological inflation occurred, what caused it? Are there any really good ones?
Well, really, just because of the nature of inflation, that it occurred before the last observable surface, the cosmic microwave background, it's actually quite hard to find out much about it. So the goodness of a model of cosmological inflation is quite hard to say at this point. As long as it explains some of the variables, some of the observables, it's good enough as far as we can tell.
And that's really where this research comes in. You've been looking at dark matter and a specific type of dark matter, which we'll go into in a moment. But firstly, tell me a little bit about dark matter.
So dark matter is thought to constitute about 80% of the matter in the universe. And the really cool thing about dark matter, I think, is that it's invisible. So it doesn't seem to interact with light. It doesn't seem to interact with matter very strongly. It doesn't even seem to interact very strongly with itself. So it streams through everything, and the only way it interacts is gravity. So it still has a mass. So the reason we think dark matter is there is through a couple of different effects, the first of which is gravitational lensing, which is just the bending of light around it. So there's been a couple of times in recent observations where we've seen this gravitational lensing effect, the distortion of light, where there's no matter around.
So there's got to be something there that's causing that.
Yeah, exactly. So there must be some invisible stuff there that we're not quite seeing. So it's not absorbing or emitting light. Yeah. Another reason why we believe that dark matter is there is due to the way that galaxies rotate. So we seem to think we know how gravity works, and if we look at how these galaxies are rotating, it seems as if there's a lot more matter holding the galaxy there than just the amount that's observable. If there was more mass towards the center of the galaxies, then it would sort of twist up much more, and you wouldn't get these beautiful spiral arms like the ones that we get. So it's not so much that there's something holding them there, it's that the matter seems to be much more sparsely distributed over the radius of the galaxy.
And this has sort of brought us to the idea of dark matter halos surrounding galaxies, and small galaxies like, say, the Large and Small Magellanic Cloud would have a lot of dark matter there, and larger galaxies a little bit less. But this brings us to dark matter halos, and this is where you've come in looking at mini halos.
Yeah, so dark matter halos are a very interesting topic because it tells us a lot about the properties of dark matter itself. If each dark matter particle has a lot of energy, then the structure that they would form would be much more smooth than the structure than they would form if they had low energy, just because they would have more energy to stream out further. So if we have what we call cold dark matter, this low-energy dark matter, and we have a model of inflation that predicts large overdensities being produced, these big clumps being produced in the early universe, you would get what we call ultra-compact mini-halos. This just means that they're these very dense clumps of dark matter of maybe less than about 1,000 solar masses that could be distributed even within our Milky Way.
And these are the things you're going to be looking for to try and help you understand cosmological inflation.
Yeah, exactly. So we've been searching for them through two main different methods, the first of which is gravitational lensing, so seeing whether they could either bend the light, so we would see stars' positions move slightly if there was a dark matter halo between us and them, or through something that's called time delay lensing. This is if we look at an object called a pulsar, which basically flashes at a very constant rate, and if a dark matter halo passes between us and the pulsar, then the lensing effect would actually slow the flashing of the pulsar down slightly as the dark matter went towards the line of sight, and then it would speed back up again as the dark matter halo passed away from it again. That's called time delay lensing.
Because the light would be traveling further to get around the dark matter halo because of the lensing effect.
Exactly, yeah. It's got to pass through the gravitational potential of the dark matter halo, and so it actually takes longer to get to us if it has to go through it.
And how's the search for these going?
Well, the fact that we haven't found them is actually a great thing too. So because we haven't found them, it tells us that the driver of inflation, something that we call the inflaton potential, doesn't produce these large overdensities in the early universe. And so we're actually able to rule out a number of different inflationary models just from that, by not observing these ultra-compact mini-halos.
Okay, so the lack of evidence is evidence of, I was almost going to say the lack of evidence is evidence of absence. That doesn't sound very scientific to me.
No, it's true, though. Not observing something oftentimes can be just as good as observing something. We've also been trying to search for them through the Fermi gamma ray satellite. So I've been saying before that dark matter doesn't seem to interact with itself very strongly. But if we say that perhaps it does, and in doing so it produces high energy radiation in the form of gamma rays, then we would be able to detect these ultra-compact mini-halos using this Fermi gamma ray satellite, the space telescope. And again, we haven't been able to observe any of them. So that, again, is a good indicator that the inflaton doesn't produce these ultra-compact mini-halos.
So what we're really doing here, I guess, is looking at all sorts of ideas and ruling them out one by one in the hope of eventually narrowing down the likelihood of what is likely to be the cause of cosmic inflation.
Yeah, well, more or less. That's how a lot of astronomy gets done nowadays, is by slowly whittling away at different models until all that you're left with is one main model. So because the inflaton field, this driver of inflation, is such a difficult thing to observe, this is a really cool new way of constraining its properties.
That's Hamish Clark from the Sydney Institute of Astronomy's School of Physics at the University of Sydney. Last month on SpaceTime, we reported how astronomers think they may have finally solved the mystery surrounding a weird erratically flickering and dimming star, whose strange behaviour sparked speculation that it could have been our first sign of an advanced alien civilization. The star, named KIC 846285-2, was first detected years ago by NASA's planet-hunting Kepler Space Telescope. However, the observations were so unusual, one scientist jokingly suggested it could be a hypothetical alien megastructure called a Dyson sphere. Dyson spheres are hypothetical massive artificial structures large enough to encircle an entire star, harvesting off its energy to power an advanced civilization. It's worth pointing out only the tabloids took that seriously. Nevertheless, more serious scientific endeavours to try and explain KIC 846285-2's dips in brightness have ranged from clouds of gas and dust to the breakup of an orbiting planet, or possibly an unusually large group of comets circling the star. However, after seeing similar behaviour in another star, astronomers eventually concluded what they were actually seeing was most likely the edge-on view of a very young star system which was still actively forming new planets. The problem is, a new study from Carnegie's Josh Simon and Caltech's Ben Montet has reopened the mystery. The researchers analysed further Kepler observations of the puzzling star. They found that in addition to its rapid unexplained brightness changes, the star also faded slowly and steadily during the entire 4 years it was being watched by Kepler. The erratic pattern of abrupt fading and then re-brightening of KIC 846285-2 is unlike anything that had been seen on any other star. Spurred by a controversial claim that the star's brightness gradually decreased by 14% between 1890 and 1989, Montet and Simon decided to investigate its behaviour in a series of Kepler calibration images that hadn't previously been used for scientific measurements. They figured the new data would confirm or refute the star's long-term fading, and finally clarify what was really causing the extraordinary dimming events detected. However, the authors found that over the first 3 years of the Kepler mission, KIC 846285-2 dimmed by almost 1%. Its brightness then dropped by an extraordinary 2% over just 6 months, remaining at about that level for the final 6 months of the Kepler mission. The pair then compared this with more than 500 similar stars observed by Kepler, and found that a small fraction of them showed fading similar to that seen in KIC 846285-2 over the first 3 years of Kepler images. The problem is, none exhibited such dramatic dimming in just 6 months, nor did any exhibit a total change in brightness of 3%. The new study, reported in the Astrophysical Journal and on the pre-press physics website archive.org, found that the steady brightness change in KIC 846285-2 was astounding, and their measurements over 4 years confirmed that the star really is getting fainter over time. The findings are unprecedented for this type of star. Astronomers simply haven't seen anything else like it in the Kepler data before. In other words, the star was already unique because of its sporadic dimming episodes. But now astronomers have identified these other features that are just as strange, both slowly dimming for almost 3 years and then suddenly getting much fainter more rapidly. Astronomers were already starting to run short of good ideas to account for the dips in brightness, and the new results will make that task even harder. Simon and Montet still think the best proposal so far for explaining the star's drastic 6-month dimming might involve the collision or breakup of a planet or comet in the star system, creating a short-term cloud of dust and debris that blocks some of the starlight. The problem is, that wouldn't explain the longer-term dimming observed during the first 3 years of Kepler data, and also suggested by measurements of the star dating back to the 19th century. The mystery deepens. New data from NASA's Cassini spacecraft has confirmed the existence of another subsurface ocean on a moon in the outer solar system. Cassini has discovered an ocean under the surface of the Saturnian moon Dione. 2 other Saturnian moons, Titan and Enceladus, are already known to hide global oceans beneath their icy crusts. And oceans are also known to exist under the frozen surfaces of the Jovian moons Europa, Ganymede and Callisto, as well as the dwarf planet Pluto and possibly also the dwarf planet Ceres. The new findings, reported in the journal Geophysical Research Letters, indicates Dion's crust floats on an ocean 100 kilometres below the surface. The readings indicate the subsurface ocean is several tens of kilometres deep and surrounds the moon's large rocky core. The study by scientists from the Royal Observatory of Belgium are based on gravitational data from recent Cassini flybys of Dione. Dione is very similar to its smaller but more famous neighbour Enceladus, whose south polar region hosts a formation of crevices known as tiger stripes, which regularly spurt huge jets and geysers of ice and water vapour into space. While Dione seems to be quiet now, its broken surface bears witness to a far more tumultuous past. The authors modelled the ice shells of Enceladus and Dione as global icebergs immersed in water, where each surface peak is supported by a large underwater keel. Scientists have used this approach before, but previous results have predicted a very thick crust for Enceladus and no ocean at all for Dione. According to the new study, however, Enceladus's ocean is much closer to the surface, especially near the South Pole, where geysers erupt through a few kilometres of crust. These findings agree well with the discovery last year by Cassini that Enceladus undergoes large back-and-forth oscillations known as libration during its orbit. Enceladus's libration would be much smaller if its crust was thicker. As for Dione, the new study finds it harbours a deep ocean beneath its crust and core. Like Enceladus, Dione librates, but below the detection level of Cassini. A future orbiter studying the Saturnian moon could test this prediction. Dion's ocean has most likely survived for the whole history of the moon, and thus it offers a long-lived habitable zone for any potential microbial life. That's because there's contact between the ocean and the rocky core. These zones of rock-water interactions provide a rich soup of key nutrients and minerals and a source of energy. All are essential ingredients for life. Dion's ocean may be too deep for easy access, but both Enceladus and also Jupiter's moon Europa are generous enough to eject water samples into space, ready to be picked up and analysed by passing spacecraft. The club of ocean worlds, that is icy moons or planets with subsurface oceans, seems to gain new members with each new mission to the outer solar system. It's all painting a very different picture from the frozen, geologically dead world we once thought it was. This year's Nobel Prize for Physics has gone to David Thales, Duncan Haldane and Michael Kosterlitz for revealing the secrets of exotic matter. The trio used advanced mathematical methods known as topology to study unusual phases or states of matter, such as superconductors, superfluids and thin magnetic films. Topology is a branch of mathematics that describes properties that only change stepwise. Superconductivity is the ability to conduct electricity without resistance, while superfluidity is the characteristic property of a fluid with no viscosity and therefore flows without losing kinetic energy. In the early 1970s, Kosterlitz and Thales overturned existing hypotheses that superconductivity or superfluidity could not occur in thin so-called two-dimensional layers. They showed that superconductivity could occur at low temperatures and also explained the mechanism, phase transition, which makes superconductivity disappear at higher temperatures. Then in the 1980s, Thales was able to explain a previous experiment with very thin electrically conducting layers in which conductance was precisely measured as integer steps. He showed that these integers were topological in their nature. At around the same time, Duncan Haldane discovered how topological concepts could be used to understand the properties of chains of small magnets found in some materials. We now know of many topological phases, not only in thin layers and threads, but also in ordinary three-dimensional materials. Their discovery meant the fewer degrees of freedom and the fewer dimensions for particles, forces and interactions to travel through made quantum mechanical systems easier to study. Put simply, equations that are difficult or impossible to solve in 3 dimensions can become much easier when only 2 dimensions are involved. By studying thin 2-dimensional layers and the topological defects inside them, new properties of matter became apparent, boosting frontline research in condensed matter physics because these topological materials could be used in new generations of electronics and superconductors and eventually in quantum computers. While few would disagree with how significant their research was in explaining the behaviour of exotic matter using the mathematical concept of topology, many were still surprised that the award didn't go to the LIGO collaboration's historic first ever detection of gravitational waves in September last year. Meanwhile, the Nobel Prize in Chemistry has gone to Jean-Pierre Sauvage, Sir Francis Stoddart and Bernard Feringer, whose research created a workshop of the world's tiniest machines, including an elevator which can raise itself 0.7 nanometers above the surface. These tiny devices can mimic many of the molecule-sized machines operating inside cells. Eventually, the trio would like to harness this nanotechnology for drug delivery, microscopic power plants and smart clothing that can adapt to specific surroundings. And that's the show for now. You can subscribe and download SpaceTime as a free twice-weekly podcast through iTunes, Stitcher, Bytes.com, Pocket Casts, SoundCloud, YouTube, Audio Boom, and from SpaceTimeWithStuartGary.com. The show's also broadcast coast to coast across the United States on Science 360 Radio by the National Science Foundation in Washington, D.C.
This is SpaceTime with Stuart Gary. For more, you can follow us on Facebook, Twitter and Tumblr. Just search for SpaceTime with Stuart Gary.
SpaceTime is brought to you in collaboration with Australian Sky and Telescope magazine. This month, looking at whether the next generation of supercomputers will be able to handle the mega streams of data expected from the next generation of giant telescopes like the Square Kilometre Array.